Okay, so today we're gonna pick up again with our understanding of the anatomy of the respiratory system. Remember last time we went over this concept of internal versus external respiration. So we know that what we're talking about is really external respiration in this unit, which is internal respiration, really cellular respiration. We also talked about different parts of the respiratory system, starting with our upper airways and going through the conducting zone of the respiratory system, where we don't have gas exchange, but do have some kind of dead air in there, or warming, humidifying the air. Then we started into our respiratory zone, where we're going to have the actual process of gas exchange happening. So that's where we are today. So the main part of the respiratory zone is made up of these structures called alveoli. So alveoli are these little bubbles, these little grape-like clusters on the tippy tips of our respiratory bronchioles. So this is where most of our gas exchange is happening. And there are about 300 million alveoli. Now, I don't recommend you pull out someone's lungs and try and spread them across the ground. But if you were to do this with the alveoli, you'd get something about the size of a tennis court. So they have a lot of surface area for gas exchange to happen. The other thing that's true is that they have a really rich blood supply. So they're almost completely covered in what might look kind of like a sheet of blood. There are capillaries all over top of the alveoli. So there's pretty much always a really close blood supply next to the alveoli where we have this gas diffusing. The other thing we have are alveolar pores. So these pores are going to allow some pressure shifts between alveoli, and we'll talk about that as that becomes relevant. For now, we're going to be thinking about what this barrier for diffusion of gases is made up of. So we're going to be thinking about the walls of the alveoli. So if we were to zoom in on one of these bubbles, one of these alveoli, singular is alveolus, we'd see that we have type 1 alveolar cells, which are basically a type of epithelial cell. So they're our main part of the lining. They're making up that wall. Scattered in and about, we do have a type 2 alveolar cell. This is going to make something called surfactant, which is a fluid. So surfactant, this fluid, is going to basically prevent the alveoli from completely collapsing. And we'll talk about that as we talk about alveolar pressures in a future lecture. We also have alveolar macrophages. So this is part of our immune system. So we're still trying to make sure that we're not taking in pathogens into the body through our respiratory system. So we saw that part of how we do that is through our mucus escalator. We have our mucus secreted by goblet cells trapping particles, and then the ciliated cells pushing all that trapped mucus up and out. We also have these macrophages in the alveoli, taking care of anything that might have gotten in. So here's a picture of what this looks like. So our picture on the left here, this is the yellow part is our respiratory system. So starting with the trachea and then all its branching. But we can see that right in front of it and paired up all the way down through all those slits, we have our pulmonary arteries, our bloodstream, and then the capillary network across the alveoli. And here we see some actual cells. So here we see an alveolus, that's this brown part. And then we see capillaries running all around the alveoli. So we're in really close contact with the blood, with the cardiovascular system. So here's that zoomed in alveolus. So our type 1 cells are the lining. So it's pointing here to this yellow type 1 cells, but really all these tiled cells around here are our type 1 cells, because this is a cross section through a spherical alveolus. So that's our lining of the wall. Then we have our type 2 cells, which are going to secrete surfactant. Okay. And then we have some macrophages here. So those are just scattered throughout. We wouldn't really consider them a barrier to gas exchange, a barrier to diffusion, because we can have the gas just go across those type 1 cells, right? That's mostly what's there. We don't really need to go across a type 2 cell. So zooming in even farther, once we're thinking about a gas particle, we're going to be thinking about it as going across the respiratory membrane. So the respiratory membrane is going to consist of that alveolar epithelium. So those type 1 alveolar cells, that's our epithelial cell layer. Then our next piece is the endothelial layer of the capillary. So just all those cells that make up the lining of a capillary. And we have a basement membrane in between. And that's it. So we have two linings sandwiched together, a little basement membrane in between holding them together. So all we need for a gas particle to do is to diffuse first across that alveolar epithelial layer, then it's in the basement membrane, and then it goes across the capillary endothelial layer, and it's in the blood. So because we're so zoomed in, this might look like a lot, but this is actually very thin for arrangements in your body. It's about 0.2 microns thick. So this is a pretty easy way for gas to get into your body. So they have a really thin respiratory membrane, making gas exchange easier, facilitating the gas exchange. So here we see more pictures. Oops, erase my old drawings. So here we're looking at a bronchiole, and because we've cut through a slice of tissue, we can see alveoli surrounding it. This is what they might look like. We can see how their walls are quite thin here, right? Very thin walls. Lots of surface area. Yep.
So, the holes that are in the picture, is that what fluid would be, or air?
Air. So those are the alveoli. Yep. So, yeah, air. So as we move forward and start to talk about inspiration and expiration, we're going to be tracking pressures in the thorax and how they affect pressures in the alveoli. So in order to do that, we need to remember or learn what the structures of the thorax are. So the thorax is your chest. So your chest wall, airtight, hopefully, right? Don't have holes all the way through your chest wall. We have a skeletal structure, so we have the rib cage and the sternum, as well as the thoracic vertebrae on the back. We also have muscles. So we'll have internal and external intercostals that we'll be interested in with respect to breathing. We also have the diaphragm, which we spoke about a little bit when we spoke about the cardiovascular system, but that's going to be the division between your thorax and your abdomen. So that's kind of like the floor of this area surrounding the lungs. The other thing to know about the lungs is that the lungs are lined by a membrane. The way they actually develop is they kind of punch into a sac-like structure. So like as they're developing, you know, sort of like a sac or a sandwich bag, and then the tissue of the lung is over here. and it starts to grow and push this bag inward. It's all growing long. Okay. So we have lung tissue with a membrane lying on top of the tissue, and then another layer of that same membrane lining the wall of the thorax. So that's what we call the pleura, is that white part that I'm drawing on the board here. So the pleura is a membrane that lines both the lungs and the chest wall, and we'll often refer to it as a pleural sac because of the way it develops, because it's this entire enclosed space. So the lung tissue has pushed into the pleural sac, which then creates this kind of folded structure. So we're going to have pleura on the lung itself, and then we're going to have pleura on the chest wall, and they rub against each other. This space is fluid filled a little bit, so that, as we see, it keeps the lungs kind of stuck to the chest wall, but there is a little bit of space in there. So, oh, for those of you on Zoom, I apologize. I should probably draw this here. Okay, so we have our pleural sac, and then the lung has punched into it. Our lung would be a separate structure here. Okay. Sorry, horrible lung drawings, but whatever. Okay. Was not trying to make that anatomically correct. So the pleura, when we talk about the pleura, sometimes we'll see things refer to visceral pleura. So visceral always refers to an organ. So that would be the part of this lining that's on the lung. Parietal always refers to a wall, like pared means wall. So that parietal pleura would be referring to that part of the pleural sac that's on the wall. So this is our pleural sac, this blue part as a whole. And in this intrapleural space, this space inside the sac, is where we'd find intrapleural fluid. So intra within, pleural referring to this pleural sac. There's not a lot of it, about 15 milliliters. Here we see a slightly better, more professional drawing. So here we're looking at a tiny little segment that we've pulled out of the wall. So this pinkish purplish part is the lung tissue itself. The blue part is referring to that pleural sac. And then we can see muscle and rib. So the intrapleural space, right, is this part that almost looks like a tube that's just showing this bag that's kind of flattened against the lungs. And you can see here that we have lining on the lung itself, and we have the lining on the inside of the chest wall. So the fluid is in the central part here, in that intrapleural space, sandwiched in between the lung and the rib. Mm-hmm.
So that pleural sac is like essentially attached to the wall and the lung.
Mm-hmm.
So
Yeah.
it's both.
Yeah, it's attached to both. It's really just an enclosed bag, and we actually don't have air come in or out of the pleural sac at all. It's inflating the lung tissue itself, so that intrapleural space, yeah, shouldn't be changing its contents. The pressure will change depending on how much physical volume there is, physical space there, but if we ever have more material, gas, or fluid go into that intrapleural space, that's a problem. Like that's when we have a pneumothorax, we'll talk about. That's when air gets into that intrapleural space, totally messes with the pressure. That's how you end up with a collapsed lung. So it's important that this is a closed container, basically. But your lung can't be a closed container, the tissue itself, because you have to get air from the environment. So now we're going to start talking about those forces, and that may clarify some of these structures as well as we start to talk about their role in breathing. So when we say pulmonary ventilation, that's the top. That's the process of moving the air in and out of the lungs, including both inspiration and expiration, which are the same thing as inhalation, exhalation, breathing in, breathing out. So as we mentioned last time, the way air moves through airways is actually going to be quite similar to how how blood moves through the cardiovascular system. So what do you think is going to be driving the airflow? Why are we going to have air movement? Exactly. So we're going to be thinking about a pressure gradient, a pressure difference. It's going to be the role of forcing that air to move. And how do you think we're going to slow the air down or change how fast that flow happens? Yeah, exactly, resistance. So we're going to see these same physical properties that we've been talking about. So air is moving in and out of the lungs by bulk flow. So we remember that we had that equation for flow. Our flow was a pressure difference divided by our resistance. So all we're going to have to add on to this to understand our respiratory system is what pressures are we talking about now? Where is resistance coming from in this system? So air is still moving from high to low pressure. Everything in the world should be moving from high to low pressure. So we're going to be going down our pressure gradient. This means that when we're thinking about our pressure gradient, we need to know which two parts of the system we're comparing. So to figure out whether air is going to go in versus out, what you're going to be comparing is the pressure inside the lungs versus the pressure in the environment around you. Those are the only two pressures that matter for this basic question of, are you inspiring, inhaling, breathing in, or are you expiring, exhaling, breathing out? The only two things you have to compare to make that decision is whether the pressure in the lungs is less than the atmospheric pressure. So that would mean we have high pressure in the environment, high atmospheric pressure would move into the low pressure in our lungs. Or we might have the opposite situation. If we have high pressure in the lungs relative to a lower pressure in our surrounding environment, we're going to go out. We're going to go from the high pressure in the lungs out into the environment.
I think the pressure that like when it's inside the lungs is it changing because of the exchange. That what changes it from high to low?
So actually, the pressure in the lungs is going to be changing because of the movement of the structures of your thorax. So like when you breathe in, you feel your chest wall move out. That is actually almost happening first. As you expand the volume of your thorax, there's a relationship between pressure and volume, or pressure and the amount of something. So when you make your chest bigger, it drops the pressure in the lung because you have that same amount of air, but suddenly it has more room to spread out. So that is a definition of lower pressure. So that's what's going to be moving it rather than the movement across the respiratory membrane into the capillaries. Because when we have that gas exchange happening, oxygen is going into the capillaries, but carbon dioxide is coming into the alveoli. So for inspiration and expiration, we're comparing pressure in the atmosphere, pressure in the environment, the pressure in our lungs. We're also going to have a little bit of air in your lungs between breaths. This is partially important because you don't want these lungs to collapse. So we keep a little bit of air in there. Also, we know that in our conducting zone, right, these pathways are just for allowing air to flow into the lungs. We don't have gas exchange happening there. So we know that that's going to add into some of these things as well. That's our functional residual capacity. We'll talk about different lung volumes and how we measure them and how we use them to diagnose different conditions in a future lecture. I did say the only two things we have to pay attention to for inspiration versus expiration is our pressure in the lung and our atmospheric pressure. Those are these first two pressures. So atmospheric pressure, that's the pressure of the environment, so the air surrounding you. Okay. The pressure that we consider the pressure in the lungs is this next one, the intraalveolar pressure. So this is going to be our pressure in the lung. So if our question is just, is inspiration or expiration happening, all we have to do is figure out which of these pressures is bigger or which of these pressures is smaller, because we're always going to be moving from a high pressure situation to a low pressure situation. We do have another pressure that we pay attention to when we're thinking about the respiratory system, but we don't need to consider this if we're just figuring out in and out. This third pressure is talking about how the lung is going to be expanding or contracting. So it is a pressure that's important if we start to think about conditions like pneumothorax. Or,
Where are the alveoli capillaries in relation to the go through it, or they
they don't. The pleural sac is really an empty space. It's just filled with that fluid.
It's on top of them, on top of the capillaries?
Yeah. And you'll probably get to stick your hand into this space in lab this week or next week and feel how it's slimy. Whether you want to feel that or not, I do recommend trying it. So the space you'll be in as we go into the thorax will be that pleural sac, that intrapleural space. And you'd have to sort of peel away the pleura to get to the alveoli and the capillaries. So yeah, that intrapleural pressure here in the pleural sac is what's going to be kind of pulling on the lungs as you use muscles to expand your ribs. This is going to exert a pull on the tissue of the lungs so that the lungs travel along with the chest wall. So that's really the role of our intrapleural pressure. And so if we measure our transpulmonary pressure, that's what we're measuring here. We're measuring how we are pulling on the lung tissue. So sometimes we call it the distending pressure across the lung wall. So this is like the pressure that's causing the lung to change shape, change size. The pressure that tells it to distend. So to calculate that transpulmonary pressure, we're no longer interested in the atmospheric pressure because we're just talking about what's happening in the space in the thorax. So we're going to compare the pressure in the alveoli, so inside those sacs in the lung tissue. We're going to subtract from that our intrapleural pressure, so the pressure in the pleural sac. And this is going to give us our transpulmonary pressure that'll tell us how strong that pull, basically of the thoracic wall on the lung is. So to recap, if anybody asks you, are you inhaling or exhaling? All you need to pay attention to is atmospheric pressure and intraalveolar pressure. But if you want to understand something about how the chest wall expanding pulls on the lungs, you might think about the transpulmonary pressure, which means you'd need to also think about the pressure in the pleural sac. So that's like an extra bit. Another thing to know is that when we talk about those first two pressures, the atmospheric and the intraalveolar pressure, since for the purposes of respiration, we're just worried about which one is bigger, we often give these pressures relative to each other. So like we're going to make atmospheric pressure 0, so we're going to subtract it. And then we'll just get a number that's either positive or negative for the intraalveolar pressure. So you want to pay attention to whether you're getting a relative pressure, which is saying that these pressures are being compared to each other, or whether you're getting an absolute pressure, in which case you're going to get numbers like 760. Segueing into here, right? So our atmospheric pressure, the pressure in the atmosphere around us, is 760 millimeters of mercury if you're at sea level. Goes down as altitude increases, the air gets thinner. If you're underwater, it increases, and you can even feel that pressure on you if you dive down. Other lung pressures, we're giving with respect to the atmospheric pressure, just because staring at numbers like 760 versus 800 or something would be harder than looking at 0 versus 40. Okay. So when we give relative pressures, what we've done is we've subtracted that 760, that atmospheric pressure, from the true pressure in the alveoli, so that we can just look at this very easily. Do we have a positive number or a negative number? And that helps us kind of tell right at a glance of what's going on. So our intraalveolar pressure, what we think of as that pressure in the lung. So it's, I'm going to draw our alveoli again. So we've talked about our bronchioles, eventually our respiratory bronchioles have these alveoli on them, these grape-like clusters. They're covered with capillaries. I'll draw some capillaries around here. And then the pleural sac would be separate, kind of a bubble that we've like pushed into. Something like this. And out here we'd have ribs and muscle. These red streaks are the muscle. Okay. Mm-hmm.
Sorry, I'm still having some grasping like the sac versus the lung.
Mm-hmm.
We see it in the lab, when we see it like rules of lung, is that just the like alveoli and stuff, and the sac is over the top, or is the sac like not connected to the lung?
So
Looking at it,
no, it's connected. So when you pull out a lung, the shiny stuff you'll be touching on the surface of the lung is going to be the visceral pleura, so the part of this sac that is like pasted onto the lung. It's kind of like the pia mater on the brain. You know how that was just like, it looks like the surface of the brain, but it actually is a different layer. It's like that.
Okay,
Does
so I
that
was
help?
just envisioning that like this is the lung, and then there was like another sac.
Yeah, we're not going to be able to pull out that sac separately. It's just a different layer of tissue. So when we get into lab, like we'll have cut in to this space when we went in with like,
Okay, so there'll be one layer on the lung, and the other layer
will still be on the thorax. Yeah. So
Right.
if you stick your hand in to scoop out a lung, your hand will be going like right here.
Got it, okay.
Does that make sense?
Yep.
So you'll probably be able to feel that the like slimy part on the surface of the lung is similar to what you'll feel on the inside of the chest wall. It does? It makes sense now?
Yeah.
Okay, good. Yeah, the idea of these sacs in the body is tricky. Yeah. So our intraalveolar pressure is if we're measuring the pressure in one of these bubbles specifically. So that's why we're calling this the pressure in the lung, right? So our intraalveolar pressure is the pressure that like an oxygen molecule in the alveolus would feel. So this is going to vary with our phases of respiration because the alveoli are going to be changing size, therefore changing pressure, and we're going to have the movement of air into our lungs and out of our lungs. So all of this is going to change intraalveolar pressure. Because we're giving intraalveolar pressure relative to atmospheric pressure, it's going to be relatively simple to immediately see the pressure gradient between the environment and the lungs, because a negative pressure is going to tell us negative that the pressure in the lung is lower than the pressure in the environment. So negative pressure in the alveoli and negative intraalveolar pressure means the air is going to come towards it to fill up the lung. During expiration, we're going to see a positive intraalveolar pressure. So air is going to escape out to the environment, escaping that higher pressure in the alveoli. So these two pressures, the atmospheric pressure versus the alveolar pressure, are what's driving ventilation, what's driving that movement of air. Our interpleural pressure is a bit of a trickier concept. This is the pressure inside that sac. I guess I shouldn't have erased that drawing. Okay. So our sac here, alveoli from our lung here, capillaries, and bronchioles leading up to the trachea and leading out. And what's there? So the intrapleural pressure is the pressure here in the sac. Okay. If we're going to look at the sac in the body, it's going to be much more flattened. So like it would look, I'm going to pick this purple color. What you'd really see is this just like sandwich layer almost lying directly on top of the lung. But it really is a space, a contained space. Okay. So the pressure in that pleural sac under normal conditions is always going to be negative. So it's always going to be a lower pressure. This means it's always going to be exerting a bit of a pull on the lung tissue. We want it to do that. We want it to have a slightly negative pressure. We want it to pull on the lung tissue because we want the lungs, the tissue of the lungs, to travel with the rib cage, to travel with the wall of the thorax. We don't want to push the lungs away from the walls of the thorax because then we're not using all our space and we're going to end up with a collapsed lung. So we want a negative pressure in this space so that we basically stick the lungs to the thoracic wall. It is going to vary a bit with the phase of respiration because we'll be changing the size of the chest, the size of that thoracic cavity as we use our muscles to pull on our ribs and as we use our diaphragm. So we are going to see it varying, but it should always be negative. This is also partially due to some properties of the tissue of the lungs of the chest wall. So the lungs are basically always trying a little bit to kind of collapse in on themselves and get smaller. And the chest wall is always trying to pull out a little bit, trying to get bigger. So these are two opposing forces pulling on that intrapleural space. So like lungs are trying to pull this way, chest wall is trying to pull that way, intrapleural pressure is going to be keeping them together. And part of why I can do that is because it does have this fluid layer. So the surface tension of that fluid, so the interaction between the molecules in that fluid, sticks the wall to the lungs so that those molecules want to stay stuck together. And that's really how we manage to keep this intrapleural space from expanding. And in this way, we get to keep the lungs moving with the chest wall. Maybe we'll look, I'll find us a video watching this in motion, and that may help sort of orient ourselves on what's going on as well. So looking here, what we've got, they're showing us our bronchioles in purple. Right, so these are our bronchioles. Here in yellow, we have our alveoli. We've indicated our intraalveolar pressure. So if it was at 760, that would be the same as the environment, which at sea level is 760. So we would consider 760 in the atmospheric pressure and in the intraalveolar pressure to be their absolute pressures, but easier to make it relative pressures. So we'd subtract away the 760 and we'd just say they're both at 0. Okay. So in this case, do we have air moving in or out of the lungs? Is there a gradient? No, there's no gradient. So at this point, there's no physical flow of air happening when these two pressures are the same. So we're at rest, but we do still have an intrapleural pressure. So the intrapleural space inside the pleural sac is this dark blue, and then this very subtly lighter blue here would be the walls of the pleural sac lying on top of the lung and on top of the chest wall. So this would have a pressure of -4, keeping that lung tissue essentially touching the chest wall. So if we wanted to calculate the force that's keeping those two things together, we take our alveolar pressure of 0, and we'd subtract our pressure in the pleural sac, which in this case is -4. And so our transpulmonary pressure would be 4. We don't need that number to figure out if air is going in or out. For that, we just need atmospheric and alveolar. This is just telling us the pressure that's kind of pulling the lung tissue towards the chest wall. That's the transpulmonary pressure. So it's the pressure across the lung, but that's not the pressure gradient that's forcing the movement of air. So, but the reason we care that we keep that pressure negative, right, is this is what happens in a pneumothorax when we open up that space, right? So here in this pneumothorax, say, I don't know what this is, a stabbing, right? So you got stabbed in the chest, right? We got into the pleural sac here. So now we have an opening. Now that pleural sac is exposed to the environment. So it's not self-contained, it's not a contained system. Because we had a pressure of -4 here, air would move from the environment towards that low pressure, towards this intrapleural space. This means suddenly we're going to get air into that pleural sac until it's at equilibrium with the atmospheric pressure. Okay. So it's going to come to 0 as well. And at this point, this means our lung is no longer going to be held against the chest wall. There's no force pulling it there. So it's going to recoil because it's slightly elastic, it's slightly stretchy. And so as it recoils and is allowed to move back towards its kind of natural smallest state. This is collapsing our lung, and suddenly we don't have room for this air to go in, and more importantly, we don't have a force forcing the lung to expand, which means we're not going to be able to change that intraalveolar pressure anymore, which means we're not going to be able to change the pressure gradient between the environment and inside our lungs, which means we're not going to be able to breathe with that lung.
So then how could you do as a lung transplant to separate the sac from like the cavity of the lung that doesn't just like wait, you know what I mean? If you're taking a lung and putting it in someone else, how do you not puncture the sac if it's attached to the lung and to the thorax? Because you have to replace like the pleural sac, right? That's part of the.
So I don't really know how they transplant it. I can come up with some guesses for how I would try to do it.
Can you remove the whole thing and still keep that like space between them?
I suspect that they probably like, just from a physical perspective, like they probably take this out of the donor, like with the one side of the pleura attached to it, and then maybe push it in from here or stitch it up. I have to look into the exact procedures for that.
So you're talking about like the inner layers will create the pressure, right?
The layer, the layer of the sac, yeah, the two things pushing against each other, yeah. So it's like, I should have brought my sandwich bag from lunch for this.
I mean, I'm getting it.
You got it. Okay, yeah, how they would do it.
If you puncture one side, how would you keep that pressure?
Yeah, I mean, I think basically you just cover up the hole, right? So like, it's not like if you get stabbed, they can never fix a collapsed lung, right? Like you can close this space over, right? And once it's closed over, you can adjust it. Yeah, yeah. So I think that's probably it. Just like you can heal from a cut, right? Right? Like it's not like once you're open forever. I will be looking up surgeries after class. You know, things we do in our quote unquote free time. Okay. So yeah, the transpulmonary pressure is that descending pressure across the lung wall, so that's keeping our lung from collapsing basically. And as we increase this transpulmonary pressure or increase the descending pressure across the lungs, that essentially means we're increasing the pull of the chest wall of the thorax on the lung. And this is how we're going to be able to make the alveoli expand. We're basically just going to pull harder. So the systems we just saw, we were looking at the fact that sometimes we're between breaths, where at rest you don't have air moving in or out. So you do still have some air in your lungs. I had a name for that volume of air. I haven't really focused on this that much. That was our functional residual capacity. And I'll come back to that later in a bit. This question let's spend some time on now. So we're given a situation here saying our atmospheric pressure is 760 at sea level. So at rest, we know that the relative pressure of the alveoli is 0. But if we wanted to know the absolute pressure, the absolute intraalveolar pressure, what would that be? Anybody want to take a stab at this? Yeah, this is the same situation we've just seen. So the reason that intraalveolar pressure is 0 at rest, all that means is that we have a situation where the atmospheric pressure and the intraalveolar pressure are equal, And they've given us the atmospheric pressure of 760. So that's how we would get an absolute pressure of 760. Realistically, from here on forward, we're going to be giving these pressures as relative pressures. You just want to make sure that you can, in your mind, relate these to pressures you might see like in chemistry classes. It's not that we actually have a pressure of 0, it's that we're giving these numbers relative to each other. Our movement is happening because of pressure gradients. So pull on the air is that pressure gradient between the environment and the intra-alveolar pressure inside your lungs. As we talk about what is causing the alveoli to get bigger and smaller, to expand and contract, we'll also be thinking about that intrapleural pressure, which we can think of as the pull on the lung tissue exerted by the chest wall. So in order to change those alveolar pressure, we also need to know some things about the muscles that we'll talk about at the end of this. We do have some explanations in your books about physics related to this. So this first part is telling us that our force for airflow, so flow, as we know from before, is a difference in pressure divided by the resistance. So in this case, our difference in pressure, instead of thinking about arterial pressure and venous pressure, this is now our atmospheric pressure and our intra-alveolar pressure that we're interested in. So that's now going to be our pressure difference here. And that's all this equation at the bottom is saying. So we could take our atmospheric pressure and subtract our alveolar pressure to get our pressure gradient. And eventually, when we start talking about different conditions, we'll also talk about resistance. The other law that we're going to see that we've talked a little bit about conceptually, but not formally in terms of numbers, is something called Boyle's law. We'll be talking about the ideal gas law. So this is the idea that pressure is inversely related to volume. So like if we have 4 little molecules in a small container, this is a higher pressure than 4 little molecules in a bigger container. And that is really the level to which we need to understand Boyle's law to understand breathing. But it is important to understand that much because we're going to be changing the size of the alveoli. And that's how we're going to be changing intra-alveolar pressure and therefore changing the pressure gradient and therefore causing us to breathe in and out. So we'll pick up with that next time with this business. But don't worry too much because we're really just thinking about the volume and the pressure part and are pretty much going to ignore the rest of that equation.